Okay, so if we are practicing chemists in the lab, in order for us to figure out how much product we can make out of a reaction equation, we need to know how much reactant stuff we're starting with. But it's not just that easy as being able to convert between the amount of reactants you're starting with and masses and just calculate the amount of product you're going to get out. One reactant is inevitably going to get used up before the other, and that reactant that gets completely consumed or used up first is called our limiting reactant. So we can quantitatively determine, aka calculate, how much product we can make from our given reactant masses through these limiting reactant calculations. So there's 4 easy steps to calculating limiting reactants, and the first is that you got to start off with a balanced chemical reaction equation. So I'm going to walk you through some examples using this reaction right here. So we have solid potassium reacting with liquid water, and when these two things react, they're going to produce potassium hydroxide and hydrogen gas. But if you look at this reaction equation here, it's not balanced as is. So we have to balance it as our first step to calculating the limiting reactant in this equation. So if you take a quick second to balance it, you should get 2 potassiums, 2 waters, 2 potassium hydroxides, and 1 hydrogen. So now that we have the balanced chemical reaction equation, we can start using it to determine which reactant's going to run out first. Is it the potassium or is it the water? So let's say you have a 2.4 gram piece of potassium and you drop it into 50.3 milliliters of water. This makes sense for the measurements to be given in this way because a potassium is a solid, so you would measure that in grams. But water we don't really often measure in grams. We use a graduated cylinder to measure out a volume of the liquid. So they're giving us here the volume of the water we'd have, 50.3 milliliters. We want to figure out how many grams of potassium hydroxide we can produce from this reaction. And then I give you an extra conversion factor as a hint that 1 gram of water is equal to 1 milliliter of water. So let's start out by just kind of analyzing the information we've got. So we know we have 2.4 grams of potassium. We're reacting this with 50.3 milliliters of water. And at the end of this problem, we want to find our mass in grams of potassium hydroxide. So the second step to calculating a limiting reactant is determining what's called your theoretical yield. And what this means is you're basically trying to figure out how many moles of product you can produce if each of your reactants were completely consumed. So you're going to do this step kind of twice. If all the potassium reacted, how many moles of potassium hydroxide could be produced? Or if all the water reacted, how many moles of potassium hydroxide could be produced? So when you're doing this step, you want to make sure you're calculating the theoretical yield in moles of your product. Don't go all the way to grams. You're not guaranteed to have choose the correct limiting reactant if you get all the way to grams. So if we want to figure out the moles of product we can produce, and we're starting out with a mass for potassium, we have to consult our mole map. So on our mole map, let's take a look right here. Erase some old stuff I've got. We're starting out with a mass of one of our substances. So on our mole map, we're starting in this box right here. We have the mass of substance A. For us, substance A is solid potassium. We're trying to determine the amount of moles of potassium hydroxide we can produce. So to get over to the moles of potassium hydroxide, we first have to figure out the moles of potassium we have. At this point, we can use this arrow to get over to the moles of potassium hydroxide, and that'll end us where we want to be here. So since we go through 2 arrows, we need 2 conversion factors. The first conversion factor is molar mass. The second conversion factor is the mole-to-mole ratio. So let's head back over here. So if we have a 2.4 kilogram piece of potassium, that's going to start out as our first known factor. So we're going to start out with our known here, 2.4 grams of potassium, and we put it as a fraction over 1 just to help us organize our process here. And we need to multiply this by our first conversion factor, which we decided was the molar mass conversion factor. So our molar mass ratio is either grams per mole or mole per grams, depending on the units you want to cancel out. So for us, we want to cancel out this unit of grams, which means we have to put grams in the denominator of our conversion factor. So we need grams of potassium down here. Up on top, it's going to be 1 mole of potassium. Remember that our molar mass conversion factor is the amount of grams always per 1 mole of that substance. So if we consult our periodic table, it turns out that the molar mass of potassium is 39.098 grams. So at this point, we've got our moles of potassium, but now we need our next conversion factor, which is the mole to mole conversion factor. This is going to take us from moles of potassium to moles of potassium hydroxide. So in order to figure out how many moles of each we're working with, we got to consult our balanced chemical reaction equation. The coefficients tell us how many moles we've got. So in this problem, we have 2 moles of potassium per every 2 moles of potassium hydroxide. So let's fill that into our conversion factor. We want to get this unit of moles of potassium to cancel, so we know it has to end up in the denominator of our fraction. So we have 2 moles of potassium per 2 moles of potassium hydroxide. And we can pause here because this is the unit we want to end up with to calculate our theoretical yield. So if you throw this in your calculator, you should end up with a amount of moles at 0.061. And so what this is telling us is if all of our potassium reacted, this is the maximum amount of potassium hydroxide we could produce. So if it's our limiting reactant, this is the amount of moles we'll get. However, we don't know if it's our limiting reactant yet because we haven't checked on the water. So we have to run this process again, now assuming that all of our water is going to react. So here we did this for K. We're going to repeat this process now for H2O. What would happen if all of our water reacted? So we know that we have 50.3 milliliters of water, but on our mole map, we don't have a conversion that takes us from volume to moles. So we have to use this extra conversion factor I put in to get us from volume to mass. So if we know that we have 50.3 milliliters of water, we can use this conversion factor of 1 milliliter of H2O to 1 gram of H2O to help us get to our mass. From there, it's got the exact same setup as the potassium before. We're going to need that molar mass conversion factor. So for every 1 mole of water, there are 18.015 grams of water. And then we need the mole to mole conversion factor. And in this equation, it happens to work out that we have 2 moles of water per 2 moles of potassium hydroxide. So it's still a 1-to-1 ratio, just like we saw with potassium. To check our units, milliliters cancels with milliliters, grams cancels with grams, moles of H2O cancels with moles of H2O. So we're looking pretty good here. If you throw this number into your calculator, you're going to end up with 2.8 moles of potassium hydroxide. So this is step 2. Determining how much product you're going to get out if each of your reactants were to completely react. Step 3 is comparing your theoretical yields. If all the potassium reacted, we'd end up with 0.061 moles of potassium hydroxide. If all the water reacted, we'd end up with 2.8 moles of potassium hydroxide. This number here is significantly smaller than the 2.8 moles. What this means is that we'll never get to 2.8 moles of potassium hydroxide with the numbers, with the amounts of reactants we're given, because the potassium will run out much, much earlier. So step 3 is analyzing your theoretical yields. Since this number is smaller, what this tells us, therefore, potassium is the limiting reactant. Potassium is going to run out first. So step 4 of your calculating limiting reactants is taking that value you got for your theoretical yield and just finishing off the problem. If I were to ask you how many moles of potassium hydroxide would be produced here, you could end at this portion because you know it's 0.061 moles of potassium hydroxide you could produce. But in this problem, I ask you to solve for grams. So we have one last step we need to do, and that's moles of potassium hydroxide to grams of potassium hydroxide. Since it's just a simple moles to mass conversion, we need the molar mass conversion factor. So we're going to take our value of 0.061 moles of potassium hydroxide, put it over 1. This is now our known. We're using the molar mass conversion factor. So for every 1 mole of potassium hydroxide, the molar mass for this substance is 56.105 grams. So we'll end up with about 3.4 grams of potassium hydroxide, and that's our final answer. Check your units, moles of potassium hydroxide, moles of potassium hydroxide. We end up with grams. That's exactly what we wanted. There's 2 sig figs we need to report our value to because we have 2 sig figs in our original problem. So this number is looking pretty good. So now from here, if I ask you to figure out how many grams of hydrogen gas are going to be produced in this reaction, there's a couple ways you could go. You already know that your potassium is the limiting reactant here. So you could do a conversion to start with your known mass of potassium and end up with your mass of hydrogen gas, or you can make use of mole-to-mole conversion factors. Notice, you know how many moles of potassium hydroxide you're going to get out of this equation. So one possible route you could take is to go from moles of potassium hydroxide to mass of hydrogen gas. If you go from moles of substance A to mass of substance B on your mole map, this requires 2 conversion factors. You're going to do a mole to mole and then a molar mass. This is option 1, route 1 on your mole map. Route 2 on your mole map is what I mentioned earlier. You could always start with your known mass of potassium, since you know that's your limiting reactant, and end up with your mass of hydrogen gas. So route 2 would be mass of substance A being potassium here, to mass of substance B. And on your mole map, this one's going to take you through 3 conversion factors. It does not matter which of these setups you decide to go with. You're going to end up with the same answer anyway. So let me walk you through both of them real quick. If you're starting out with your moles of substance A, you know from your limiting reactant equations, calculations, you're going to start out with 0.061 moles of potassium hydroxide over 1. Then to get to mass of hydrogen, you first have to do a mole to mole conversion factor. So from your balanced chemical equation, for every 2 moles of potassium hydroxide, you have 1 mole of hydrogen gas. So 1 mole of hydrogen gas per every 2 moles of potassium hydroxide. Units here are going to cancel out. Now that you know your moles of hydrogen gas, you can take this and you can convert it to a mass by using the molar mass conversion factor. So for every 1 mole of hydrogen gas, there are 2.016 grams of hydrogen gas. Again, units cancel out. Throw this in your calculator and you should get 0.062 grams of H2. Alternatively, you could go back and start with your mass of potassium, which are given in the problem. So you know that in the problem, you're starting out with 2.4 grams of potassium. This is your limiting reactant. You can get to moles of potassium by using the molar mass conversion factor. So in 1 mole of potassium, there are 39.098 grams of potassium. And here, units cancel with the units. Now to get from moles of potassium to moles of hydrogen, you would need to use a mole to mole conversion factor. So if you look back at the balanced chemical equation, for every 2 moles of potassium, there are 1 mole of hydrogen. So 2 moles of potassium per 1 mole of hydrogen. Last step, now that you have moles of hydrogen gas, you got to get the mass out of that. So this would be a molar mass conversion factor. In 1 mole of hydrogen, there are 2.016 grams of hydrogen. Again, units here, cancel with units here. Plug this in your calculator and you're left with 0.062 grams of H2. And these two numbers are equal. Yay! So it doesn't matter at this point which route you're going to take. There's a couple different ways you could go. So as long as you get your conversion factors right, you should end up with the same answers. But for calculating limiting reactants, you've got to go through those same 4 steps. Step 1, get your balanced chemical equation. Step 2, calculate your theoretical yield. Step 3, choose the smaller value to identify your limiting reactant. Step 4, finish off the problem for whatever you're asked.